Hello everyone, I am Untitled. In this video, we will solve one problem in chapter 22. A charge of negative capital Q has been deposited uniformly a circular arc. A. Find the electric field vector at the origin. According to the figure, dq is the differential charge on the differential circular arc length ds, which is calculated by r times d theta, where d theta is the differential angle. Also, theta is measured from the negative y-axis, and we accept this direction as negative. So, the other side is positive. In order to find the electric field at the origin, we assume that there is a positive test charge at the origin. Since dq is a negative charge, the electric field is drawn from point O to dq. Now assume that there is another differential charge dq on the positive side. Since it is negative, the electric field is drawn from point O to dq. And due to symmetry, their x components, e times sin theta, cancel each other. Thus, we are remained with their y components, which are e times cosine theta. Therefore, the net electric field vector at the origin for the whole arc is calculated by the integral dE times cosine theta negative j hat, because it is in the negative y-axis. dE is calculated by the formula k times dq over r squared. And because k and r squared are constant, they can be taken outside the integral sign. So, we are left with negative k over r squared integral of dq times cosine theta j hat. In order to progress, let us find an expression for dq in terms of theta. The line charge density of the circular arc, denoted by lambda, is calculated by the formula dq over dl. Here, dl is ds. From this, dq is obtained as lambda times ds. Since charge negative capital Q has been deposited uniformly, then lambda is also calculated by the formula total charge over total length. According to the figure, a circular arc length L is calculated by the formula 1/3 2 pi r, where 2 pi r is the circumference of a circle of radius r. Therefore, lambda can be written as 3q over 2 pi r. So, dq becomes 3q over 2 pi r times ds. From the previous figure, ds is r times d theta. Therefore, dq becomes 3q over 2 pi times d theta. Therefore, if we write this expression into the formula for the electric field, we obtain negative k over r squared times integral of 3q over 2 pi times cosine theta d theta j hat. And because 3q over 2 pi is constant, it can be taken outside the integral sign. So we obtain 3k times q over 2 pi r squared times the integral of cosine theta j hat. Here the integral variable is theta, which is between negative 60 degrees and positive 60 degrees. Here the integral of cosine theta over theta is sin theta. Therefore, we have the electric field negative 3k times q over 2 pi r squared times sin theta, between negative 60 degrees and positive 60 degrees, and j hat. Therefore, we have negative 3k times q over 2 pi r squared times sine 60 degrees minus sine negative 60 degrees, j hat. We can write sine 60 degrees as root 3 over 2. Also, sine negative 60 degrees is negative root 3 over 2. Therefore, the electric field becomes negative 3 square root of 3 k times q over 2 pi r squared j hat. B. If you put a charge negative q at the origin, find the force vector acting on it. The force vector is calculated by the formula negative q times E, where negative q is the newly coming charge and E is the old electric field at the origin. Therefore, we have simply 3 square root of 3 times k times q over 2 pi r squared j hat. That is, this is a repulsive force. Okay, this is the end of the discussion of this problem. Thank you for your attention. See you in the next video.